Okay, Dr. Sandeep. Good morning, all. Today I'm going to discuss briefly about the radar polarimetry for understanding the microphysical processes which are especially utilized in the core monsoon zone. So this is the layout of hierarchy. Many of the people might have already known this one.
How is not same? 70 kilometer tower. Which very long. Oh,
Okay.
Easy. Okay.
Yeah. From the pioneering work of Professor Silochana Gadgil, so it's well documented the spatial distribution of monsoon rainfall, as well as the following by Rajavan et al. And Pai et al. How that spatial variability during the intra-seasonal oscillation, like active and direct spells and wet and dry spells, has been well understood over Indian domain. So apart from this, even the spatial distribution of different or various precipitation systems has been well documented by Robert House and its group. Just shown one sample picture, like saying that the deep convection is dominated over Himalayan region, whereas the stratiform and wide convection has dominated over Bay of Bengal region. All these studies they have well documented as with respect to seasonal aspect as well as the regional aspect. Also, they even studied the regional aspect, like especially the Himalayan region, Himalayan belt, as well as the other Indian domains. Like Murali Krishna et al., they have studied the interannual variability of these various precipitation systems over the Indian domain. Like they also included the shallow convective part, which they have left over this by House and et al. Group. So they have included the shallow convection also. Shallow convection, then stratiform, and then deep convection, and then wide convective core. How they are spatially distributed during the monsoon season, like different interannuals, like how a positive TBO and how it will vary in the negative TBO period, all are well documented over the Indian domain. And then recently, Das et al., they have studied the same spatial distribution of various precipitation systems during the passage of synoptic scale disturbances such as lows, depression, and deep depression. So all these studies, they have already well documented the spatial distribution of rainfall or precipitation systems over the Indian domain. However, the vertical structure of this precipitation system, especially the microphysical aspects, was particularly lacking over the Indian domain. So that's why we are carrying out this exercise to understand what are the dominant microphysical modes.
See this round stake that is from satellite.
Yes, TRMM data set. In addition to that, Goswami et al. 2006, they have highlighted the frequency of extreme rainfall events, as well as Roxy et al. 2017 also they have highlighted the increasing the frequency of heavy rainfall or extreme rainfall event, especially over the central Indian domain. So in order to capture this kind of or forecast this kind of extreme rainfall event, one should have intense observations with collocated observation as well as the modeling. We need to have a kind of intense observation campaigns along with the prediction models, like weather prediction model runs to exactly predict or give the forecast for this kind of extreme rainfall or heavy rainfall events over the Indian or central India region. So with this aim, so IITM has established the atmospheric test bed over the central India. So here, if you see that central Indian domain, this is the contour shows the passage of the low pressure system or synoptic scale disturbances over the Indian domain during the monsoon season. All these dots represent the initiation of this LPS or synoptic scale disturbances. All these systems initiate in the head Bay of Bengal and then propagate towards the northwest India through the ARTCA central India. That's why we have selected the ARTCA in the main the heart of the core monsoon region. So this is critically selected over the core monsoon region just to capture all these synoptic scale disturbances over that core monsoon zone. And the major objective of this ERTCI is to improve the process level understanding of these convective storms. So with this aim, to understand the process level, like what is happening background these convective systems or different types of precipitation systems. So we have utilized these ERT measurements such as this radar measurements along with other in situ measurements also to illustrate or to find the background mechanisms underlying these different precipitation systems. Of course, this shows the topography. This star mark indicates the location of the ERT. Of course, I have shown one small front view of this ERT here, and this circle, whatever this shows the 250 kilometer of coverage of the C-band radar, which is installed here. The C-band radar is installed on the top of this tower, around 20-meter height tower, and it is operational from almost July 2021 to till now continuously without any gap. And then along with this, we have another suite of measurements like aerosol measurements in the laboratory as well as the atmospheric radiation observatory, and then cloud and precipitation observatories, including dieselometer and then other radiometer, other radars also. Okay, so this is a widely accepted and well-known methodology to classify the precipitation systems and to understand the dominant microphysical mechanisms right now. So as of now, people mostly utilize this dieselometer measurements. Like I have shown here one example, like using the HSCPL dieselometer observations. So where we have classified the precipitation into two categories, like stratiform as well as the convective systems, using the Bringy et al. 2003 or 2008 algorithm. And then from this, we adopted this Dolan et al. 2018 technology or methodology framework. So just to infer the background or dynamic, whatever the dominant microphysical processes that is behind this stratiform as well as the convective precipitation. Like Dolan et al., they have utilized the DSD measurements from 6 different regions over the globe along with the radar measurements, and they have given a framework like showing the dominant microphysical mechanisms behind each and every rainfall systems. So like if you see here the convective system, this red portion and right shade portion, all this is convective systems, and then convective precipitation mostly dominated by the ice face region. And then of course, if it is a weak or shallow convection, then it will be a majority will be like the collision covalence will be dominated. Whereas if you take the stratiform portion, the stratiform may contain like aggregation or timing along with vapor deposition and other major microphysical phenomena. So this is the easiest and widely accepted methodology to understand the microphysical mechanisms. Yeah. Recently, Murali Krishna et al. 23 or 26, they have adopted the PCA-based approach, like principal component analysis based approach, to identify the like dominant modes of variability. What are the dominant modes, like different modes of variability inside this rainfall? So by using that same dieselometer measurements over Mumbai, they have identified 4 major modes, like I have shown here: group 1, group 2, group 3, group 4. So 4 major modes of rainfall variability, and they also find that so each group have different microphysical mechanism, like I shown here in the space of D0 and log NW space. Like these are the dieselometer measurements. So these are the gamma DSD parameters, and if you put these 2 parameters, then you can have a D0 and NW space. Like if you see 4 groups have different microphysical mechanism. This group has aggregation or timing dominated, whereas this is dominated by the collision processes, and these are the like weak convection, which is dominated by almost like breakup or evaporation processes, whereas this another weak stratiform dominated by the vapor deposition conduction. So all these can be inferred from using this dieselometer measurements. But the limitation of these dieselometer measurements is it will give only the dominant microphysical mechanisms, but it cannot actually infer the what is happening behind each and every type of precipitation systems. And the second thing is these are the in situ measurements or ground-based observation, so that the whatever the information, whatever it is giving, this may have or it is biased towards the microphysical mechanisms which is happening in the rain region instead of the what is happening above that region. So in the ice face region. So for that purpose, we need to have a vertical measurement or like a remote sensing observations to have a nice picture of what's happening behind this each and every system. So for that, we have taken this radar measurements. Radar observations over ARD, and then we have give a detail about all these microphysical mechanisms that is happening over the behind this precipitation system. So before going to the detailed observations and results, I just try to introduce some of the radar parameters, basic parameters, because most of the students may not be having that much idea about all this radar measurement. So if you take the conventional radar, which is a single pole radar, so it will emit the signal or radiation in one polarization, like horizontal polarization, and then it will receive the same horizontal polarization. And using that return signal, we can estimate the radar reflectivity, radial velocity, as well as the spectrum width. This radar reflectivity will be the amplitude of the return signal. That means depends on the size and shape, whatever maybe all the information, how much precipitation is happening or what kind of system it is there. You can just infer from the reflectivity measurements. And then Doppler radial velocity, Doppler velocity, it will give the motion of the system, either coming toward the system or radar or going away from the radar. And then spectrum width will provide the turbulence present within the each resolution volume, radar resolution volume. So this is a conventional radar system. But in addition to this, suppose if you want to have a like microphysical understanding of this system, then you need to have a dual pole. Cross section about idea about the horizontal plane only. So whatever happening in the along the horizontal direction only, you can have observations, but you will miss the vertical observations. So to have this kind of thing, so you need to have a dual pole measurements, dual pole radar, in which emits the radiation in two directions, like a horizontal plane as well as the vertical polarization. So both planes you can have a measurement. So you can transmit both, and then you can receive both, so that you can have a measurement along the horizontal axis as well as the vertical axis, like as shown here. This is. So with this dual pole measurement, you can have a like other observations like differential reflectivity, differential phase, and then correlation between the horizontal as well as vertical measurements. Like I'll give each and every one. So this differential reflectivity, which is can say ZDR, it is represented by ZDR. If you take it in a logarithmic scale, it is simply the difference between the horizontal as well as vertical radar returns or reflectivity. So reflectivity in the horizontal as well as reflectivity in the vertical. So that if you subtract the two, then you will get the information about the shape of this raindrop. Yeah, this I have shown here. This is. Yeah, this is. So you can give the shape of this shape information you will get from this differential reflectivity. So suppose if the raindrop is whatever the precipitation particle is spherical or near spherical, then it is ZDR should be almost 0, because whatever the horizontal measurement as vertical measurement, both will match each other. So difference will be almost 0. Suppose if the raindrop it deformed from the original sphere, if it is oblate or prolate shape, then the reflective ZDR will vary. Suppose if this is a horizontal element, it means prolate oblate particles, then the ZDR will be positive. If it is a prolate particle, vertical element, echoes or targets, this will be very much low. So you can simply segregate these either precipitation or non-precipitation using this rho HV measurements. So all these like ZDR, KDP, or rho HV, these are very much essential to identify or to understand the background microphysical mechanism. Like I just shown here an example of this radar scan, PPS scan, that is the reflectivity and ZDR, KDP, and all. I'll give more detail after reading my talk. Yeah. So before utilizing this radar observations, because this is a C-band radar, so the attenuation is a little bit here is the cannot neglect the attenuation because of the rainfall. So we have corrected these radar measurements before proceeding further for the rain attenuation using Z5 method. And then of course, if you look at this plot, so this left side, these two are the reflectivity and Z and ZDR before correcting just measurements whatever we have taken from the radar. And these are after applying the attenuation correction algorithm, like these are these things. So if you see this radar reflectivity like enhanced after the first, like after crossing the first rain cell, the reflectivity decreases here. In similar way, ZDR also has been decreased. After attenuation correction, all this you can see the enhancement in the reflectivity as well as in the ZDR also you can clearly visible. And one more thing, after attenuation correction, you can able to see this bright band or melting layer structure very clearly in this ZDR measurements compared to the raw observed material differential reflectivity. So now coming to this microphysical studies, just have given one. Initially, I'll just go through one heavy rainfall system which occurred over this ART site during 22nd August case. So I just want to give a broad overview of the system. So this one shows that this data has been collected from the ERA data, ERA file. This is the geopotential height as well as the horizontal wind at 50 hectopascal. You can see clearly a low pressure system with cyclonic circulation is present over this ART site on that day, 22nd August. And if you see the OLR, so low OLR over this central India radar domain indicates that formation of a typical deep convective system over that region. And that this GPM has recorded almost more than 150 mm of rainfall within 24 hours. Whereas this disrometer, in situ disrometer, measure almost 240 mm of rainfall over the same ART site on that day. So from this, it is clear that GPM is a little underestimating the rainfall over not only central India. It's well known that GPM is underestimating the rainfall. And satellite measurements like pointed out by Anton sir, like GPM or whatever maybe, they also can infer the microphysical aspects. But the major limitation of that is it is a overpass. So it will not continuously monitor the given region. It will have certain overpass like 16 hours only it will come. So if the system present that time, then only you can have the observation. Otherwise, you will miss the observations. And in the monsoon period, you will have frequent passage of these synoptic stage disturbances or precipitation system. We will going to miss a lot of things in the using the satellite measurement. So that's why these in situ measurements are very much essential to understand or continuously monitor these kind of precipitation systems. So again, this is the same like one of the snapshot of ZDR, KDP as well as the rho HV during this passage of this 22nd August low pressure system over that ART site. And I have shown here this. Suppose you can see here wherever the high reflectivity regions are there, the KDP is very much high. That means it is indicating that higher liquid water content or higher rain rates are present over this region. As you see, I'll give you more details. So right now, suppose if you want to see whatever I have shown here, this is the PPA image, plane position indicator map of this radar variables. Like whatever the radar will scan, like what elevation, then it will cover the 360 degree azimuth. Like it will have a measurement over 360 degree. So one such elevation azimuth map I have shown here. Suppose if you want to see the vertical cross section of this any precipitation system, this may not be helpful for to see. It will give a aerial coverage or spatial view of the system. Suppose if you want to construct the vertical structure, then you have to construct a quasi-vertical profile because it's not exactly the vertical profile. That's why we call it a quasi-vertical profile. By taking measurements at certain elevation angle, like let us say 10 degree or 20 degree elevation, and then taking the azimuthal averaging, then we can construct a vertical profile of this precipitation system or whatever data repose over that radar domain. The center will be radar, and then you can take a 10 degree or 15-20 degree azimuthal elevation and you take the azimuthal averaging. So this is one such kind of a quasi-vertical profile that is constructed during that day, like 21st August to 22nd August from 18 UTC to 18 UTC, like 18 UTC of 21st to 18 UTC of 22nd August are shown here. Now, if you see the vertical structure, you can very clearly it can show the differences in this within the precipitation system. Like if you see the top one, reflectivity, it shows almost like uniform reflectivity in the time or maybe in the vertical also. There is not much variation in this one. So that is a major limitation of the single pole system. So you cannot infer any microphysical processes using this one. But of course, you can see very clearly a bright band signature. The bright band is the thing that near melting layer at 0 degree isotherm. So the radar will have the return reflectivity, will have higher rate cost. Like return echo will be very much severe. That we call it as a radar bright band or radar sorry, bright band only. And this is, you can see only the bright band structure is clearly visible during this 12 to maybe 15 or 16 UTC period. Except that you cannot infer much from this reflectivity measurements. But if you see the polarimetric measurements like the ZDR, differential reflectivity, or KDP, you can see very clear differences within the system. Even if you see here, there is an enhanced KDP between like 5 kilometers to 8 kilometer region here, and then again here there is something like that. And if you see here, there is a very low ZDR values between like around 5 kilometer region. And if you see here, there is a very clear signature of bright band or melting layer in this Rho-HV profile as well as in the ZDR profiles. All these will be clearly you can identify using these polarimetric measurements. So now I'll detail the microphysics like each and every event. Like I have considered like 3 events here. This is first event where the KDP measurements are very much high. This is one region, one domain I have taken, and the other domain I have taken this one where ZDR is very minimal over this region. And another one more, if you see here, after 6 to maybe around 11 UTC, the precipitation echoes does not cross this 0 dB isotherm, which we call warm rain or maybe probably shallow rain region. All these three things I will give each and individually. I will explore the microphysics, how it is behaving, all this with using this radar as well as with some other in situ measurements. This is for the first event, which I have shown the higher KDP. That event, these are the CFATs, contour frequency by altitude diagrams, constructed from using this reflectivity and differential reflectivity and KDP. So if you can see here, there are certainly differences like vertically. If you see, this is the beauty of the radar, which you can give a vertically resolved information of the precipitation system. Like if you see the top at around maybe 9 kilometers to 8 kilometers around this region, the ZDR is almost constant. It's not varying much in that height region. Whereas if you see that same height region, this ZDR is increasing, whereas the KDP is also increasing. So this could be because vapor deposition might be dominating that region because of the vapor deposition. Vapor deposition onto the ice crystal is a low density particles will originate over that region, and because of the low density as well as the low aspect ratio, the ZDR is almost will be same. It will not vary much. Whereas because of the vapor deposition, the particle size will enhances. So the increase in the particle size will be reflected in this KDP measurement. That's why the KDP is increasing over this region. So the increase in the KDP as well as the almost close to zero, same without any deviation. This is ZDR. This infers the probable vapor deposition over that region. That means this is, you can say this is almost like a region close to cloud top, where the cloud particle forms. Ice particles will be forming over this region. And now coming down to this 8 kilometers or close to 7 kilometers, the ZDR becomes maximum, and then KDP is still increasing over that region. So the ZDR is maximum in the sense the particles are horizontally aligned. So when the particle is horizontally aligned, then the value will be positive as well as high. So it means in this region, the horizontal ice crystals, that's what we call dendrites or plates, might be forming over that region. This is a region where the dendritic particles are growing. And the region of maximum KDP around in between like 10 to minus 15 degrees C domain. So this is the region where the maximum concentration of dendritic particles will be available. So that is the reason why this maximum KDP is showing here. This can be called as a dendritic growth region. And we can see that there are 5 vertical velocities. Like in this region, like around 8 to 6 kilometer region, there is some small positive vertical velocity as updrafts are present over this region. And you can see here, this is the radiometer derived relative humidity. There is some sort of increase from below 6 kilometer to above 6 kilometer. There is some sort of increase in the relative humidity. That means this vertical velocity will simply push that available moisture. Thereby, supersaturation will occur during this in this region, and this supersaturated height will collide with the or freezes onto this ice crystal, whatever may be the like aggregated particles which are developing over this region, dendritic particles. Thereby, the size of these aggregated particles or dendrites are increasing. So that is the reason why this KDP is keep on increasing and reaches the maximum at around 6 to 7 kilometers in this region only. That means this region is what we call the dendritic growth region or dendritic growth layer. There is a kind of dendritic particles. The concentration of dendritic particles will be maximum at that region. That is indicated by this KDP measurement. And coming down to this like 6 kilometer or whatever will be after this KDP maximum, this KDP is decreasing. Similarly, ZDR is also decreasing in this region, like below 7 kilometer region. So this is probably because when that dendritic particles are horizontal aligned particles coming down, so they will again collide to each other, and then they will freeze together, and then because of this collision, the particles will tumble and they will rotate. So when they are rotating, so the effective axis ratio or obliqueness or probabilities, whatever may be, the effective, because if you have n number of like it's a kind of a Gaussian distribution again, so n number of particles will be there. If the particles are rotating within that section, so effective ZDR will always be decreasing. It will come close to, I can say it is close to 0 only. So that's why if you see here that in this region, so the ZDR decreases and reaches almost close to 0, and KDP is also decreasing. So that means this region below this KDP maximum region, so the particles will, the ice particles will collide together, freezes together and forming a larger particle. Thereby, that is this is the process which the particles, ice particles collide and aggregate together is called the aggregation. That means this is the region where below 6 kilometers, this is the region where the aggregation is dominating during that period, that precipitation event. And coming down to like 5 to 4 kilometer region, you can see a very good signal enhancement in the radar reflectivity here, as well as the increase in this ZDR also. You can see this is the signature of the brightband, typical brightband signature that is very much clearly visible in this ZDR profiles. And coming down to rain region, so below this melting layer or brightband, so you can see a slight increase in the reflectivity. There is also a very gradual increase in the reflectivity, as well as slight increase in the ZDR, as well as slight increase in the KDP. You can notice here the increase in the ZDR or KDP. The ZDR increase in the sense the particle size is increasing. Similarly, if you see this KDP increasing in the sense liquid water content or whatever the particle size is simply increasing. So it will happen, even Z also increasing. That indicates that possible collision covalence between the two raindrops. So the collision covalence process simply increases the reflectivity as well as the ZDR also and KDP also below the rain region. Of course, here this increment is not drastic. It's very small, as well as it's a gradual. That means the collision covalence is it doesn't have any much vertical turbulence is not in the vertical region. So that's why the particles, while descending towards that ground, they may collide together and then form the bigger drop. That means this collision covalence process are dominating below this 3 kilometer region. So all these like vapor deposition to dendritic growth region and then aggregation, then down to collision covalence process, all these processes can only be inferred with the availability of dual pole measurements. So this is a kind of sorry, I forgot to mention this one. This is during aggregation or rhyming period. This ZDR decreases and KDP decreases. This is a textbook definition. This is, and of course you can see the same feature in our dual pole measurements also. Z is increasing this 7 to 5 kilometer region. ZDR is decreasing, whereas KDP is also increasing and then decreasing. So all these like our observations matches very well with this theoretical aspects of this microphysical processes. Now we'll move on to the second region, which I have shown that low ZDR around 5 kilometer region. And this is like if you see here, this is again the same plot, ZDR plot I have shown here. So if you see like after 12 o'clock, maybe that melting layer is around this region is a melting layer, and then after this 12 UTC, the melting layer came down little bit, and then again it has increased a little bit. I mean, it again decreased its original height. This decrement of this melting layer height is what we call the sagging of the melting layer, or melting layer sagging. And if you see here, almost the melting layer thickness is almost equal to 1 kilometer. These are the upper level of this melting layer. So melting layer will never be crosses 1 kilometer. It's almost less than that. But in the case of the melting layer sagging only, this will happen. The highest thickness of this melting layer, and that melting layer will come down during this period, which we call as the melting layer sagging. And of course, I have shown this same profiles. Like one profile I have taken here, and one profile before that one. Like this is a dotted one is the profiles during that melting layer sagging, and solid one are the without sagging. Now you can see very clearly this decrease in the height of this maximum ZDR. So between these two, as well as even this is the rho h profile. So rho h we also can see here, and then this is the reflectivity profile. You can see a very clear bright band signature during this one, and no clear signature of the bright band during non-saggy period. And if you see this decrement, so almost it is 500 meters, it has come down. The melting layer signature has come down to almost 500 meter down during this period. And suppose if you see this plot again, like here, the ZDR, if you see almost negative or close to zero during this, at this height levels, just above this 0 degree isotherm level. So these are ZDR values are almost zero or negative. And like if you see the radiometer profile, this is a cloud liquid water obtained from the radiometer, and at the same height level, like 5 to 6 kilometer height level, there is a small dip in the cloud liquid water content. So that means whatever the aggregated particles, as I mentioned earlier, when they are descending towards this, melting layer down, coming down. So this encounter with the supercooled liquid water, and then thereby they freezes onto the aggregated particles. The process of freezing the supercooled water onto the aggregated particles is called the riming. So it means this the region where this low ZDR, negative ZDR, that region indicates the riming region. That because of this riming, that means whatever the available moisture, that is simply freezes onto the ice crystals. So that's why the radiometer shows the small dip in the cloud liquid water content over that region. And if you see the MRR, micro rain radar, vertical particle velocity, is almost at this region 12 to 16. The particle velocity is almost like 2 meters per second. These are 2 meters per second in the sense the particle size will be bigger. When the particle size is more, then only it will descend with faster velocities. So it's at the upper end of this. Ice crystals will never reach that 2 meters per second velocity, and only the larger ice crystals will only can reach this 2 meters per second. The riming, whatever the process of riming, that is simply increases the mass of the ice particle, because again freezing of the supercooled liquid water onto the ice crystal, that will simply increases the size of the ice crystal as well as the mass of the ice crystal. When the mass of the ice crystal increases, then the fall velocity also simply increases. So all these features, like whatever the low ZDR and negative ZDR, is if you combine with this radiometer and then other measurement, then you can clearly infer that this sagging of the bright band is happening because of this riming. So when the riming happens, the particle size will increase. So in order to melt that completely, it will take more time, larger time, so that it will travel the larger distances. That's why the thickness of this melting layer increases at this region, at this period. Yeah. This is as a whole, I have shown like whatever I have discussed earlier, like aggregation, riming, all the periods all together. I have shown the same here, XZ, ZDR, KDK. So whatever, these are the DM and NW, the DSD parameters, whatever I have derived from the radar measurements, and these are the derived from the micro rain radar, derived from the are estimated from the micro rain radar. And if you see both, they're matching almost one close matching between the drop size in the vertical from the radar as well as from the MRR. This is simply even concentration also. You can see here the raindrop size is higher at the surface because of the whatever the ongoing collision and covalence process below the melting layer. And even if you see here the 4 kilometers also, the particle size raindrop is, DM is directly infers the raindrop size only. So here it is higher in the sense the drops are lot bigger. That bigger particles are coming because of the aggregation as well as riming. Both aggregation and riming, that increases the mass of the ice crystal or the particle size, so that when it melts, the raindrop particle size also will be always more. So that's why the larger particles are coming. And then if you see below 2.53 kilometers, again there is an increase in the raindrop size. That is because of the collision covalence process. All these processes you can see from even in the same MRR also. And the same thing I have plotted here from the densitometer in situ measurements by taking the DM and log and W space. And see if you see that DM is maximum DM and concentration will be higher towards the larger diameters. That means this heavy rainfall case contains the larger drops. That is partly because of the process of aggregation and riming above the melting layer, and partly because of the collision covalence process below the melting layer. So all these processes you can infer from this thing. And of course, these are all independent measurements. Like this is a radar, C-band dual pole radar, this is a micro rain radar, and this is a densitometer, in situ densitometer. But all together as giving the same information. Now coming to the third case, which I have shown that warm rain or shallow rain region. So here I have shown the profiles of all the same things again, but if you now I have restricted only up to 6 kilometers because there's a shallow depth of the system, so I'm not going to talk about this higher altitudes. And simply I'll talk about the maximum only and below 4 kilometers in the rain region. Here if you see the profile is entirely different if you compare to other earlier one. Earlier it is almost uniform below 4 kilometers, whereas if you see the profile here, this is not like straight line, it's gradually increasing. In similar way, ZDR also increasing higher compared to earlier case. And even if you see the KDP, a clear enhancement in the KDP, it will show. I mean, here there is no maximum ice phase processor absent, but the only mechanism that is happening, causing the raindrop growth is the collision covalence process. Because of the collision covalence process, the Z is constantly increasing, CDR is also increasing, as well as the KDP is also enhancing below the melting layer. So it means the majority, whatever the shallow convection or warm rain process, this is a dominant microphysics where the particle grows or enhances below the melting layer. And it's again same thing. Like if you notice the difference between that earlier plot and this one, earlier disometer measurement, here if you see, these are concentrated only at the higher drop sizes, whereas this, if you see here, yeah, size is reduced, but concentration is increasing. That means smaller particles are more. Majority here compared to earlier case. Earlier case, all the particles are larger particles. That's why the DM is higher and the concentration is lower. Whereas here, if you see the DM is lower, but whereas concentration is higher, this peak came here. That means this indicates the presence of more smaller drops in the this kind of precipitation. Yeah. So till now I have just discussed the only one case of this heavy rainfall event which we have observed over the IIT site. Whether this is the same, this process are frequently occurring over that region or during the precipitation systems. We just want to see, so that we have taken one season of data. So before proceeding further, we just take those radar measurements and then disometer measurements. Initially, we have classified the rainfall or precipitation systems over that region to different modes using the same PCA approach, whatever I have shown earlier. So now we have applied the same PCA approach for this IIT disometer measurements. And then we have find out again 4 modes of major modes of variability, like type 1, type 2, type 3, type 4 I have shown here. And if you see the differences among all the 4 types I have given here, like if you see the DSD, type 1 has the smaller concentration and the lower drop size, whereas if you see the larger drops are only present in the type 1 measurement. Whereas if you see the type 3, concentration of small drops will be very high. Like here I am showing diameter as well as this is a concentration. And now this is a concentration, number of particles present in the unit diameter interval of different volume. So this is the number of particles, the smaller number, like diameters below 1 mm are dominating in the type 3 rainfall, whereas the rainfall drops dominating above 1 mm are dominating in this type 1 rainfall. So similarly, type 2 and type 4 also having intermediate to those things. And then if you see the rain rate, so type 1 will have the maximum rain rate associated with them, whereas type 2 has the least rain rate, they are confined below 5 mm per hour, whereas this type 3 and type 4 is the intermediate. And if you use the rainfall contribution also, type 1 is contributing a majority of rainfall over that region compared to all other 3 domains. That means what I am just going to highlight here is whatever the modes or rainfall types we have classified, they have distinct feature. They are not overlapping with each other. So all are entirely different. If you see either this one or this one or this one, all are entirely different, saying that this PCA can, it's a robust technique which we can use it for the precipitation classification, or you can segregate the modes of precipitation. So now after classifying this precipitation systems using the disometer measurements, we have taken the corresponding radar measurements. Like in the type 1, what are the available radar measurements, the similar type 2, type 3, type 4, we have collected, segregated all the radar measurements. And then we will see the polarimetric measurements. Like I told earlier, this is the type 1 having higher rain rates. So this is similar to convective like precipitation over the tropical region, whereas this, if you see the very, very small rain rates and with very small drops, this is a kind of a weak stratiform precipitation. Whereas this third type is intermediate, you can see highest concentration of smaller particles. This is a typical like orographic kind of precipitation which we can see in the Mahabaleshwar region or orographic HSCPL region. And type 4 is the normal like stratiform rainfall over the open oceans. This is this kind of these are features are similar to the exact one. So that's why we have also named the same as it is. Like first type 1 I have shown here. This is similar to convective features. And you can see here again the same thing, like if you see the reflectivity, so the effect of reflectivity, there is no signature of the bright band during this event. So this is the main feature of the convective. So there is, you cannot identify any bright band signature with the convective systems. So there is no feature of the bright band. And if you see the reflectivity, the surface reflectivity increases almost 40 dBc. That means intense rainfall present during this type 1 precipitation. And even if you see around 4 to 5 kilometers, the 30 dBc echoes are present. That itself indicates the vertical like updrafts and downdrafts. KDP also, so higher KDP when here, and then again decreasing towards below 10 kilometer, and then here ZDR also. It is again initially it is a constant up to 7 kilometer. This is the same again vapor deposition. Again, this is a. I am not going to into detail again. Same thing repeating. So this is indicates the process of rhyming. Same thing. So that means in this convective like precipitation. So rhyming is dominating in this one. And if you see this diameter like DM profile from the micro-rendered. So again, you can see the same like below 2 to 3 kilometers. Again, this constant increase in this one. This also you can see a constant increase, and here also there is increase in the KDP. So all these increases the increase in the raindrop size or by the collision covalence processes. All this. So this is a type 3 precipitation which I have shown earlier. This is a type 3 which we attributed to mixed convective stratiform or transition or kind of a orographic kind of precipitation. Like if you see here, the reflectivities are weaker compared to earlier one. But of course, more or less it is showing the same kind of signal only. Like it is gradually increasing. But here the echo is very much weaker compared to the earlier one. That's why we call it as a mixed convective stratiform, because it has a small feature of the signature of the bright band also, a little enhancement of reflectivity at around 4.5 kilometer per kilometer, but there is no clear signature of the bright band, as well as its most features are similar to convective. So that's why we classify this as a mixed convective stratiform precipitation. And this if you see the KDP, it is very, very small, indicating that available liquid water content is very much small during this kind of a precipitation. This is a kind of a like a decaying convective system. So at the end of the convective system, so there won't be much available of liquid water content, so that the drops will be always smaller. So that's why the concentration, I mean, the small drops are dominating during this kind of a precipitation. And if you see the below this melting layer, the Z is keep on increasing, whereas ZDR is interestingly here ZDR is decreasing. ZDR is coming down. That means the particle size is decreasing during this kind of precipitation. So what could be the possible reason? Then we have see the MRR DM also. Even in this DM profile, so you can see a small decrement in the particle size, like raindrop sizes during this type of precipitation. Then we just saw this radiometer derived reflectivity again. Now if you see this below like 0 to 1 kilometer within the boundary layer, there is a drastic decrease in the humidity or moisture. That means the dry conditions prevail within the boundary layer. This because of the dry condition or unsaturated air, whatever the falling raindrop, they might be evaporating. The evaporation may happen there or may causes the decrease in the size of the precipitation particle. Thereby, this ZDR is decreasing during this period. So this maybe probably evaporation or sometimes maybe breakup also may happen during this period. So this is why mixed convective stratiform will have always the smaller drops. Even the bigger drop, if it evaporates, becomes small drop. Or bigger drop, if it collides and break down, then it breaks into n number of smaller drops. So that's why the concentration of smaller drops is always higher during this kind of precipitation. And coming to the type 4, of course I skip the type 2 precipitation because type 4 and type 2 more or less look similar. As I said, that's a weak stratiform and this is a stratiform precipitation. And the features are almost like similar to earlier one. And you can see here very clear signature of the bright band. Here or here. So earlier in the convective, there is no signature of bright band. Then mixed, there is a slight signature. And then if you see the stratiform rainfall, there is a clear signature of bright band. Again, the same thing like vapor deposition and aggregation is dominating over this region. Even there is a high ZDR, like ZDR of 0.5, that is itself is indicating that larger drops are dominating during stratiform precipitation. The same thing you can see here also. So the surface again larger drops are dominating. So altogether, I just have shown in one picture. Like these are the all 4 types of precipitation. You can see the same features like earlier, as I said, is no bright band signature here too, straight bright band to bright band signature. And then here also same thing. So availability of high moisture content during the type 1 precipitation or convective like precipitation, that is giving the larger drops in this particular period, whereas the evaporation may possibly causes the smaller drops in the type 3. And then again, collision covalence may favor in the type 4 precipitation, that again leads to the larger drops in this stratiform kind of precipitation. Yeah, just I'd like to summarize all the observed phenomena over this central Indian IIT region. Like at the top of the cloud, like we can have a major vapor deposition will favor, that will simply start the formation of the ice crystal, and thereby the ice crystal size will increase by the process of either aggregation or priming. These two are the major dominant one. Aggregation is dominating the stratiform rainfall, whereas priming is dominating during the convective type of precipitation. Then at the melting layer, all these particles will melt together, and then it will descend by descending. They'll form the raindrop, and below this region, below the cloud layer or cloud base, around the cloud base, these cloud particles or raindrops will collide together and then form the larger drops. The collision covalence process will be occurring. All these are the just sample. I mean, like all together is a picture of summary of the microphysical processes that is occurring over this IIT central facility. This all the whatever the information I have presented, all collected from this mostly from these 4 papers. Those who are interested, we can go through this publication so that you'll get information. And if you have any further doubts, also you can contact me either online or offline, whatever. So with this, I would like to conclude, and thank you.
Thank you, Dr. Murali, for putting so meticulously what you do at ART. And people like me who don't work here also got so much essence from here. So that actually gives that you are a good teacher also.
Thank you.
I totally got it. So on that note, let's open for some discussion. I would some student questions. Let's take, because I totally get it, because then students also should get it.
Hello, sir. It was a nice presentation. I just have a question. First one is that in Dolan 2018, they classified into 6 groups, but in your paper you have classified into 4 groups. So I want to know the reason why you have reduced to 4 groups. And the next question is, when we are running PCA, we mostly the TSC information will give in 1 minute resolution. And when you compare that with a vertical profile of the radar, so your radar vertical profile is like 1 minute resolution, or?
Yeah, very good question. Huh? Okay, this coming to first thing, like in that Dolan, they have considered global DSTs, a wide variety of precipitation systems, and here if you see, the concentration is very much smaller here or here or here or here. This corner thing now, they are very, very small. So we can able to see this is the dominating one here. This is the one major portion, the first stratiform region, which is dominating, and this is the third one is also very much dominating, and this is. So this is up to our thing. Like whatever the things here, you can clearly see 4 major modes of precipitation occurring over our region. Whereas if you go for other region, it may be different. Maybe you can get more or less also. Either you can go for 3 also, you can have 5 also, 6 also, depends upon the what are the types of precipitation present over that region. So in our region, wherever if you see that either Mumbai or HCC or maybe central India, so all these are like 4 major modes are dominating in the precipitation system. That's why we have taken all the 4 things. And of course, you may have a doubt of this 5th one also. There is a small here, and this is more or less same to the 3rd one. These are not, very much compared to 3rd one. So that's why we omitted that one also. So we have considered only the 4 categories. There is the first one. And coming to the second question, like exactly the DSD or disdrometer measurements are from 1 minute, whereas our C-band radar is having a resolution of 6 minutes. So what we have done, we have taken the 6 1-minute samples within the radar measurement, and then whatever the dominant mode in that 6-minute sample, that we have considered for the analysis. Suppose if either 2 or more modes are dominating, then we omitted that complete 6-minute profile or 6-minute DSD measurements. So we have taken the simultaneous, both when this is available and this is available, then only we have taken. Other things we have eliminated.
Yes. Thank you for that wonderful presentation. So my doubt is like, are there any attempts being made to derive vertical heating profiles from this suite of hydrometer classification? Are there any attempts being made to derive one?
Yeah, we are about to do, but it's not yet attempted. That will do. So slowly, one by one. First, we have come to this conclusions. Then slowly, we'll start that kind of.
So I was thinking that there are like derived heating profiles based on satellite data, like ARM or GPM. So since this is ground based and it might give a better hydrometric classification.
It's already attempted. Because yes, maybe sir will be having something.
No,
Domain.
we have not attempted those. We have a clear idea that we are going to launch like 3 locations at least reduce one day, and then we can derive the heating profile. That has been done, I think, over the tropics in the GET experiment and then in the Dynamo experiment. Right now, we have not attempted because getting that water permissions and other kind of that is tedious job. Once that is been done, we can derive all those.
It will be interesting.
Yeah. But surface radiation is there, we can directly get your heating. But what you are referring, I know that heating profile.
Really, very nice talk. I just have some doubt. Your radar is and JWD, both are located at the same place, right?
Yes.
So how do you attribute, because it is not looking vertically, I understand. So you're assuming that there is always homogeneous rainfall over the entire area, and because all this seepage or whatever you have drawn, you're covering entire area and
No.
considering that.
No, sir. That's we didn't consider the entire area. Like as I said earlier, we have taken the radar center, and then we have taken a sample, a cone of this much, and then we have taken observation only within that cone. So whatever the QVP I have constructed, that is just within the small cone area. So it's not like entire
As a vertical.
Yes, vertical. It's almost like close to vertical only. So I have taken all these are from the same QVP measurements, not the entire radar domain. It's not the entire radar domain.
Yeah, and another point here is PCA based classification. Do you think it is also dependent on the instruments? If you do classification using 2 DVD, you may get 6 groups also.
Again, each and every instrument has certain limitation. You cannot say 1 to 1. Yeah, maybe, but the thing is, you can get the same 4 dominant modes. Like I am telling here also, if you want to go for the smaller threshold value, like I will tell you. So here we have taken a threshold value of 1.5 to segregate into different modes. Suppose if you take one standard deviation, then obviously you will get 1 or 2 more major modes. But the thing is, they all have similar features. Like whatever the thing present in the central area, this region, this is like an ambiguous region where we have the features similar in all the kind of precipitation. That's why if you go for a lower threshold value, like if you go for 1, 1.5 or 2, or maybe what if you change the thing, if you go for lower threshold value, then you will get obviously more modes, but the mode separation will be like they are overlapping. You cannot clearly distinguish between the 2 modes. But if you go for a higher threshold, even 2.5 also, then you can clearly separate the major modes. But the problem is you will have a less number of data points. So in order to this kind of
maybe just one last question. You're identifying LWC profile. So when below 0 degree isotherm are considering as LWC and greater than 0 degree isotherm. So what is your confidence level that they have isotope content and they may have supercooled water, or you're just considering as it is? Because at some places you say because of the super saturation, your LWC increase, right? And WR. So how do you attribute? I mean, what is your confidence level?
Yeah, that's why I have initially I have shown this humidity profile, relative humidity, here. Then this is the like what you said earlier, like sound mix of all the things. So that's why we come to liquid water content. All the things.
Considering that. in one of more you talk about the evaporation. I think in the board that's right. Yeah, in that reflector is also increasing in that.
Yes.
And in that lower level KDP is also higher. So is that kind of some kind of cedar feeder?
Okay, this is it's not kind of cedar feeder mechanism. That increase in reflectivity, I can say that reflectivity is proportional to d power 6. So it's always weighted towards the larger drops. Like if you have heard about the any time Professor Chandra's lecture talk, he will show on cube if you put a 3 mm raindrop, 3 mm raindrop, and 21 mm raindrop, always the 3 mm one raindrop will have high reflectivity compared to 20 small raindrops. That means if you have a one larger drop, then the reflectivity will be always higher, because this is biased towards the larger drops, d power 6. So that is the reason why here it is increasing. And KDP, of course, the same thing what I'm saying is also like presence of a small larger drops. Right? That's what I'm agreeing. So maybe a few larger drops might have present, but the major thing is the evaporation. That's why the ZDR is showing constant decrease. So DM profile also is showing that.
But corresponding to that evaporation, that reflectivity does not need to get that much.
No, that will
Need to be there.
that's what like, presence of the larger drops. I cannot completely omitting the larger drop. I'm not saying that the larger drops are not at all present. Some of the larger drops are present because of this fewer larger drops, the reflectivity is increasing because of the bias towards the larger drops.
Any more questions? So now the modeler, as a modeler, I am now actually not question, not solution. I am actually trying to understand that. Okay. So first of all, that the idea of the stratiform rain and convective rain. So I am getting. Thank you very much that you have explored all these things. And lastly, you have shown another thing, the stratiform rain, the bigger droplets. So you could go to the Dolan figure, the slides. Yeah. So you can see the stratiform rain you are talking about here, that the smaller droplets, the definition of the stratiform, and the bigger droplets. But you ended up that stratiform also bigger than drops. That's the so nice. Actually, all stratiform rain is not a smaller droplet. Exactly. The DVZ is a factor. So if you notice that, you have shown that convective, then wings, and then so one cloud, then the stratiform rain. So we call it stratified basically, not the stratiform. The stratiform rain, we are that bright band will be there. And that is the thank you so much, because that clarity I also means from the modeler point of view, we only get that when the mix phase is there and there. So that now if I wrong, that just correct me, whatever understanding I have. So this is one thing. Second thing that you are talking about that LWC, and many people are asking. So you are talking about that evaporation. I feel that breakup is more, because if evaporation is there, so LWC will be more rather than that LWC is less. So you mentioned that breakup is another possibility. So perhaps that breakup might be more efficient rather than the evaporation. And another important just understanding I'm trying to get from you, that you are talking about the bigger droplets. Just curiosity that when the bigger droplets will be domed, how you corrected the attenuation, and whether it will impact on your measurement to get the bright band correctly.
We are correcting in the rain region, so in a completely ice space we are not going to correct things. But whatever you say, radome effect.
Yeah, radome effect. Yeah, radome.
Yeah, we have done.
So you have corrected. Yes. So radome effect is gone. So no need to worry about that.
Yes. Rain we have corrected for the rain.
Oh, okay. So lastly, as a modeler, we need some clear statistics of that warm top convective you have shown and cold top convective. Actually, this is a new definition now in Sumikar also, that new. So can we get that type of classified cases, more statistics of only the cool top convection and the warm top convection? Can we take?
Yes, sir. Yeah, I will.
Yeah.
Yeah. I'll come.
Yeah.
From one by one.
Yeah.
So first thing what you have asked is stratiform is having like smaller drops, and then convective will be having. Even if you see the thing, that depends upon the intensity of precipitation. So suppose if the aggregation is more favorable, or rhyming is favorable in the ice phase or mixed phase region, then obviously the aggregation and rhyming leads to higher particles,
Exactly.
larger particles. So when it melts, it will be a larger drop only.
Yes.
So that's why the region here, this region, even this comes under the stratiform region. So suppose if the aggregation is or rhyming is not efficient, then the drop size will be small. And will be, that's why here this region is dominated by only vapor deposition. If the only vapor deposition and aggregation and rhyming are very less or minimal, then the particle size or raindrops will be always smaller. If it is there, then the particle size will be increased. That is the first.
Why I am saying that model has a overestimated of the light wave, but whether it is linked with the that warm rain or it is linked with the ice testing. That's why I am asking that where the modeler will target. So you have shown in next slide, you have already shown that. See that right that. So your stratified is in the right side. So and that is you have concluded later. So my question is that as a modeler, which one will target? Whether we will target the warm phase microphysics or the ice phase microphysics to improve the stratiform. Because you know that stratiform and convective rain ratio is model is just ulta. So too much convective rain and too little stratiform rain. How we can look from this? That's why
it's a kind of like what I can say. Both are equally important. I cannot rule out any one phenomena. Suppose if you see, obviously in the stratiform precipitation, so the absence of vertical updrafts, I mean, minimal. So not okay, so absent, minimal. So the chance of getting collision covalence collision covalence may happen, but breakup may not be that much. The efficiency will be very small because of the absence of the vertical updrafts. So, but at the same time, collision covalence possibility chances are there. But a similar way, what I said earlier, suppose if the aggregation or rhyming efficiency is less, then you need not to worry about this process. Then majority will be there only. So vapor deposition will cause the small drop particles. That's it.
So as a modeler, we have to look at what is the top of the cloud, and accordingly we have to modify both warm microphysics and the ice wave. Last question. Yeah.
And coming to the second question. Yeah, here whatever third. Even in this, I also say that both the things, evaporation as well as breakup may also happen. But why I am adopting it evaporation? Suppose if breakup happens, then the number of particles will definitely increase. N will be higher. When the particles increase, number concentration increases, the KDP should increase. The KDP is not increasing here. The KDP is either same, or it is, suppose if you come down to 3 kilometers, it's more or less same only. It's not increasing. But as he said, like there is a small peak here. That could be because of the breakup.
But both look into the arrays.
That's what both the things are happening, but we cannot exactly quantify with the available things. It will have some more maybe. I think.
So last is that the shape. So that is also we are now parameterizing the shape of the ice. So the ice aspect ratio, if it is greater than 1 or less than 1, is equal to 1 is equal to sphere, otherwise the non-sphere. You are talking about that only the dendrite. Why not it is the columnar or plate? Because that what in the modeling we are doing, we are putting the third moment as the ice shape, which basically giving the columnar or plate. So and you are telling the mixed phase zone that is in 10 to 15. They are mostly dominating by the dendrite.
Yes.
So how you conclude that one? Why not the columnar and plate?
So suppose if you come to the columnar things, that ZDR should be negative because the vertical measurement should be higher, horizontal will be smaller. But whereas if you see in all our cases, there's always is a positive ZDR. That means there is.
But is it not that Hypex is object? Okay, so that they have shown that columnar particle is there. Photometer is here. So that So it is not the present in that, because I want to check the model fidelity to get the right shape.
Yeah.
So that's why I'm asking.
So as per the radar point of view, if the columnar particles are there, then it should be the ZR should be always negative only. I mean, the domination of this says here, like dendrites are plates. Like as you said, plates also could be possible, but the exact separation of plates and dendrites is a bit difficult with this only radar also.
Yeah.
But if you see here, the values of this ZR, whatever I have shown, this ZDR and KDP values here.
So the model is giving, it is not negative, it is giving the less than 1.
That is the as model perspective,
Yeah.
but if it is the radar perspective, so if both are same, so we are taking the in the logarithm scale difference, x minus y. Let's say if I take x and y axis.
Yeah, my model is taking the moment. So moment of the cell. So the growth of the moment. So that ratio basically is aspect ratio.
Yeah, that is aspect ratio. Yes.
So that is giving the less than 1, which is called the column.
Yes.
And greater than 1, place.
Yeah, that's correct. If you talk about the aspect ratio, that is on the linear scale. What you are saying, that's why it is 1 you are taking. But this is a logarithmic scale. I said earlier, like if you take in the logarithmic scale, ZH minus ZV. So in the logarithmic scale, it will go to 0.
So we can call the dendritic also.
Yeah.
Oh, thank you, Mil. Very nice.
Can you just go to the mixed convective? What? Yes. What Anupam was asking whether how much contribution we should have on microphysics. Clear picture. If you see that at 4 to 5 kilometers, sudden dip is there in the relative humidity. So that clearly shows that there is a dominant congested clouds which degrades, and that increases the background because it's a depletion of water. And then at the same time, if you see about 6 kilometers, there is increase. Its microphysics is also important in white for microphysics. Mukul was asking one question in heating profiles. Just one update very recently started 6 or 7 because mostly the latent heating profiles are based on the lookup table. So there are some methods using we are trying to modify those lookup tables based on this sheetful data. So at least some latent heating profile based on the observed data.
We are also doing that, is doing that tau algorithm. We are modifying the cloud condenser to latent. That also we are same thing, the reflectivity and cloud condenser. We are calculating the latent heating using the tau algorithm.
So your last question, the ratio of warm rain as well as this one. So we can able to, like as I said, we can distinguish also, we can separate out also using different algorithms. Simple technique like I shown one of my slides. I just mentioned one sentence like collision covalence is dominating about 51% of this one. So in this way we can segregate like using different methodologies. Like I have used here ZDR ratio and all this space application. Then we can estimate at least what is the major fraction. Whether it is a warm rain or like if you say this one, this is a like if it is dominating, then we can say warm rain is also.
We'll replace few that cases events is there so that we can look the statistics of the observation and understand the model flow.
Yeah, it's a very nice talk. I really enjoyed it. The whole idea of bringing you from there to here to present this, the excitement that I saw from people. That is the whole idea is that.
I've seen you satisfaction.
Okay, so when you come to the classification, still have some doubts. Go to the classification slide. Okay, so first tell me what is the percentage of variance explained by both this one and this two together?
Together 96%.
96.
I
Then
didn't show that.
Type 3 is the static top, correct?
Type 4 and type 2 are stratified.
So if you put them together, how much it will be percentage? Only less than 10%, correct?
Okay.
So, but throughout our.
Yeah, I'll clarify, sir. Whatever, as I said earlier, so whatever that is in here, that will go with all these things because they have a mixed features. You cannot able to clearly separate or distinguish whether it's a convective or it's a stratiform or it's a weak stratiform. So this is the kind of it's a mixed kind of. They have the features similar to either convective or stratiform or blah blah. So that's why we. Then we just there's one thing like you can say use the radar data itself, like vertical measurement. Like as I said earlier, if the breadband signature is the simplest, even that is a main which followed by TRM and GTM also. So they identify the breadband signature. If the breadband signature is not present, then they'll take it as a convective or weak convection or shallow convection. Then depending upon the vertical velocities and all, they can estimate that. I mean, they can segregate. So in a similar way, that is also possible. Yeah, this is.
But as far as we modelers concerned, we always say that 60 to 40 is what we are targeting. So now from this, I'm getting a different.
Yeah. One more thing, if you see, add up, this is the 60% what you say, convective is 60%. And if you add up all other things, because whatever 60-40, there will say only stratiform and convective only. There won't be any other systems.
So if I add all the four of them, 70%, right?
Because some of the things we limited already. So if you add this and this together, then that ratio will be like 40. You said 60-40, definitely will go.
So that middle part is actually more estimated. Yes. Second thing that I looked at profile. Shown in the.
Yes, sir.
Here. So the A is graphite, correct?
Yes, sir. Yes, sir. Yeah. This is the radar. These three are radar only.
So we have written here that vertical velocity shows up dots or melting layer. In the graphite. Whereas in the battery, don't show it much up. Right? That is what you have tried to tell. What is this between here? Small increase between 68 kilometers.
Yes, sir. This is a repeatability is increasing. But I'm telling here, this is a small graphite shows some small updraft here, this region, and this is a small increase in the
Not much.
not much, smaller. So that means available liquid water content is relatively smaller. That means what I am trying to say is the two ice crystals, they are collide together and they will freeze on together. When you join together, that freezes. That's what like I just want to say here the aggregation is more dominating compared to rhyming. So in the later case, I showed like a depletion of cloud liquid water. There is a dip in the cloud liquid water content because that is why it's happening. The collision of the supercooled water onto the ice crystal is favoring. That means that is rhyming. Whereas here there is not much change in the liquid water content and this vertical updrafts also you can see. That means the two ice crystals collide together and then they are phasing and then forming the larger crystal. Here aggregation is more favoring, whereas there it is a rhyming is favoring.
So now the way you look at aeroplane, I think you should look at models of IITM. See where is it actually fails. This is the message has to go to models. Then only they will show working.
Yeah, sure.
Otherwise, this gap is increasing every day.
Sure, definitely, sir. Next time we'll take that and we'll consider.
He is asking you data. Ask him also data. Model data. Yes, let's look at that. And this is the problem.
Sure, sir.
Okay. Very good. Still have some more specific.
Yes, thank you.
Okay.
Thank you, sir.
And one more, actually, whenever art people shows systems and all that, so you are having not actually fitting into the logic. Yeah.
That's
the logic. Yes. Somebody will get doubts about it. That's not proper.
You cannot change the sites.
Change the logic.
Any more questions? If not any, let's thank Murali for his wonderful talk.
Okay.